I'm very sure that at the end of this section, you have value for your time. So, Mr. Dapo, please, you're welcome. The floor is yours. You can introduce yourself and start the meeting outrightly. Thank you very much.
Okay, so you can all see my screen, right?
Yes, sir.
My screen showing.
Yes.
Yes, yes.
Okay.
Yes.
Okay, good. So you are all welcome to this webinar where I'll give a very as simple as possible introduction to machine learning as it's related to regression. So my name is Adedapo Adeniran. I'm a computer science graduate, data scientist, and an AI software developer, a writer with over 7 years of professional work experience in the educational, real estate, IT, health, and life sectors. I'm currently a cargo, notebooks, and dataset expert, and recently got this top data science and data mining voice on LinkedIn. It's a big grade on GitHub with over 100 stars on my repository. And I have some certificates in data science, artificial intelligence, machine learning, Python, SQL, and C# with hands-on experience on tools such as Tableau, Power BI, Excel, Microsoft SQL Server, BI Suite, Python, and some C# tools, majorly focusing on Microsoft tools because they work hand in hand. So leaving the serious introduction aside, these are some fun facts about me. Sorry, someone's background is, someone's mic is on. Okay. Just a minute. Okay. Okay. So let's move on. So some really fun fact about me is that I wrote my first book in primary school. It was a horror book, but I didn't get to publish it. I was almost a straight A student in high school, short by English and biology. And I was really, really interested in further maths. Further maths was one of my top subjects in school, especially calculus. I just love calculus a lot. And I started independent Python programming in 2015 outside of my university work. And in 2022, I decided to start reading some book summaries on my own because I wanted to increase my general knowledge. And then I taught myself how to read and write French on my own because I wasn't really taking it seriously when I was in secondary school. And I finished about 8 different paid courses within 6 months. My daily routine includes mindfulness meditation, learning French, tech upskilling and refiling, journaling, and reflecting on my day and listening to music on Spotify. If you'd like to reach me outside here, I'm on Cargo, on Twitter, LinkedIn, and GitHub. My username is BrainyDabs. So now let's get to the meat of the matter today. What exactly is machine learning? You might recall from your secondary school days when you were learning maths, learning some abstract topics like matrices, calculus, and other subjects that does not even have any connection whatsoever with real life. And then you are now wondering that why do they have to take us through the torture of going through all these abstract mathematical concepts? Well, now is the time for us to see the relevance of these mathematical concepts like calculus, matrices, regression, and the rest, because they build the foundation for modern technology and machine learning. Now, consider some of the things that you can do with your phone. For instance, if you are using an Android phone and you notice that anytime you move it on a piece of food, your phone will bring up a fork and knife image to show that it's detecting that that is a food in front of it. I don't know if you have such capability on your phone, or if you are typing on your keyboard and then your keyboard start predicting the next text you are going to type even before you are done typing it, that is AI working in the background. And I'm sure a lot of you now have Meta AI in WhatsApp where you can access it and you can even generate image directly on your WhatsApp. That is AI in action. Or if you are the type that watches Netflix, you notice that sometimes Netflix gives you a recommendation, a movie recommendation that is different from another person's Netflix. That is also AI working in the background. Or if you are the type that listens to music on Spotify, if you play this DJ, this Spotify DJ, that is also AI working in the background. All of these impressive applications are powered by mathematical principles that has been programmed into the computer to make them learn. So now you might be wondering, how do all these math concepts like algebra, matrix, calculus, how do they make a computer intelligent or even capable of learning? So before we can make a computer intelligent, we must define what intelligence means in mathematical terms. Before the computer can understand what intelligence means, we have to break it down in mathematical terms. Now, you might be wondering, why do we need to break things down to mathematics for a computer to understand? The thing is, everything you do on your computer, whether you are sending a text message to someone or you are browsing the internet, everything the computer does is just simple calculations, additions, subtractions, sometimes multiplications. Sending a text message might just be series of addition, series of subtraction. Everything a computer does is just calculations. So for a computer to understand you, it must be in mathematical terms. So the first challenge of artificial intelligence is answering the question, what is intelligence exactly? Most people are going to agree with me that intelligence is the ability to learn. If you can learn from your experience, from your past experience, that means you are intelligent. And this straightforward definition provides a foundational basis for creating intelligent machine. Now, the next challenge was to define what is learning. You've already said that intelligence is the ability to learn. Now, what is learning? How can we determine when learning has occurred? Fortunately for us, we also have mathematical tools for measuring learning to determine if learning has taken place, to determine how much learning has taken place, and to determine if learning has occurred to its maximum. Now, the mathematical principle that determines when learning has taken place is called the loss function. And there are so many formulas that can be used as the loss function, which is determined by the problem you are trying to solve with the AI or the question you're trying to answer with the AI. A very common loss function that is used in regression is called the mean squared error, MSE, which is given by this formula that we have on this screen. Now, the mean squared error, what it does is that it calculates. Let me open this graph. Now, what the mean squared error does is that it calculates the distance between a data point and a line. Now, let's take this red. Let's say this red line, or wait, this black line. This black line is the perfectly fitted line for this data point. Now, this graph you are looking at here is just a 2D graph. This is a 2D graph, which is defined by this formula, y is equals to mx plus c. That's what defines this graph that you are seeing here. All these multiple lines that you are seeing, this green line, the red line, the black line, and the green line, they are the attempts, the multiple attempts by the machine learning to fit a line on all the points that is here. You're trying to fit it to touch as many points as possible. Those points are in the data set that is used to train the AI. I don't know if you understand what I'm talking about here. Now let's go back to this slide. So all of this calculation is being done on the individual data points within our data sets. Now, there cannot be an AI without being trained with data sets. Remember that we say that intelligence is the ability to learn. And in order to define learning, we must break it down to mathematical terms. So how will a computer know that it has actually learned? And what is a computer learning from? That is the question. A computer can only learn from a data set that has been provided. You know, you as a human being, as you are going through life every day, you are learning from the things that is happening around you. You are learning from what you see, what you hear, what you listen to. But a computer cannot actually see the world the way humans see the world. So we have to give a computer its own world to learn from. So the world of a computer, where the computer learns from, is in the data set itself. A data set is usually in a tabular form. A data set is usually in a tabular form, and it can come in different formats. It can come in a CSV format. It can come in a TSV format. Usually the most popular format is CSV, which is a comma separated value. I don't know if you're still with me. Yeah?
Yes, can you hear
Can I
me?
what? Yes, I
Can
can
you
hear
hear
you.
me? Okay,
Yes,
I
I
think
can.
someone can also observe is that your screen is not too clear. I don't know whether it's your internet connection. Maybe you need to share, unshare and share your screen.
Oh, my voice is not clear.
No, your voice is clear, but the screen is not too clear. I think it's your internet connection.
Okay,
Maybe
the screen.
yes, maybe you unshare and share your screen.
Let's see. What about now? Is it showing? Can you see my screen now?
Not that it's not showing, but it's not.
It's
sharp.
actually blurry, sir.
It's very blurry.
Oh, okay. Okay. Okay, it's very blurry. Let me see. I don't know if I can
I think
increase it a bit. I'm coming.
the notes shared earlier can
What's the
be
notes?
helpful.
Let me see. Trying to see if I can increase the size here. Or let me zoom in a bit. What about now? Is it better now?
It's just blurry. Although the other time you were trying to show the slide, it was clear. Later, it just become blur.
Oh, wow. What about now? Is it better now? Can you see what's written on the screen now? Because I increased the size a bit.
I'm not sure it's about the size. I think it's the
Yes, it's not about
The
the
internet.
size, it's
connection.
the clarity.
Wow. Let me
Mr.
see then.
Dapo,
Yeah.
Dapo, what you are sharing is the same content that is the same note that has been shared in the WhatsApp group.
Yes,
So if you can,
it's the same thing.
people can follow. But that what I am following, I cannot see the screen, so but it's the note I'm following.
Oh, okay. I'm coming. Let me see if I can like share. Let me see if I can. Okay, I think I know what's going on. Let me see. Just a minute. I'm thinking because I'm not sharing the particular window. That's why it's not clear like that. I'm coming. Might be the reason, or it might be the internet, as you said. But can you people follow the note I sent? The note, the Google Colab
Yes, sir, we can.
notes itself. Okay.
Yes, it's good.
Is it clear now, or is it blurry?
It's still very blurry. I think it's the internet. So just go ahead and then people will follow the note I share on the WhatsApp group.
Oh, okay. So I've actually been okay if I should. I'm thinking, wait, let me stop sharing and start sharing again. I'm coming. Let me try. What about my face? Is my face blurry?
No,
Your
your face is not blurry.
Okay, I'm going to be sharing the windows now. Now I'm sharing the window itself. Is it better now?
Yes, yes, very clear now.
Yes,
It's very clear
it's
now,
better
Abi.
now.
Yes, yes.
Very clear, sir.
Okay, good, good. Because I wasn't sharing the window. So now this is the mathematical formula that the computer uses to know if learning has occurred or not. Now this yi, let's start with this. What does a machine learn? We will come back to this formula later. Now, what does a machine learn from? Like we said, a computer does not smell, hear, taste, or see or feel the way a living person does. So what does the machine learn from if it does not learn from the world? That's where data set comes into place. Now, that is usually a structured data that contains data information that is appropriately labeled for a machine to understand and manipulate. So data is how a computer senses and understands the world. Now, when you take a picture on your phone, for instance, the camera captures light from the outside world and it converts it into multiple pixels that are placed next to each other to give you a picture format, which can be in JPEG. When someone asks you to send a JPEG or send a PNG, that's what they meant. If you zoom in into a picture, for instance, you will see tiny boxes that makes up the picture itself. Each of these pixel is just strings of character. It's like just writing A, X, C, B, D, E, F, H, G, H, X. When you zoom in into it, that's what you're going to be seeing there. And each of these character is also a string of binary that the computer actually sees and understands. So the raw form of a picture does not make sense to a human eyes except a computer. So the same thing applies to when you take your phone and you record your voice with your smartphone. Your microphone sensor, those sensors are the things that are connected, are the components of your phone that allows it to take in input from its environment. What happens? It detects the different vibrations in air. You know, when someone is talking to you, the reason you are able to hear them is because there's vibration in the air. The vibration in the air is what is making you to hear what someone is saying to you. So the microphone sensor in the smartphone is also capturing this vibration in the air and converting it into an audio data that is going to be saved as an MP4 or M4A. There are different formats for audios too. So anywhere you send that file to, the computer or your smartphone will be able to play it. Now, in a single, even a 5-second audio file can contain numerous data in it. So an audio file is an example of a multidimensional data because it has a really large array of numbers that are stacked together side by side, and the computer just reads everything once and plays it out to you as a sound. So these things they are just being arranged together as different amplitudes that are placed together that will make the computer knows what is going on and play it back to you as a sound. So everything you do on your computer is just data. Every file you send, every picture or every video, even websites that you visit, they are all pieces of data that the computer sees as binary. And you all, assume you all know what binary is. Binary is just ones and zeros. That's what binary is. That's the only number that a computer can understand, 1 and 0. A computer does not understand 2, 3, 4, 5 that we humans understand, not to talk of text itself. So we need to convert everything in the data. Everything needs to be converted to binary before the computer can actually manipulate it and use it for its process. Now, you might have noticed something. Everything you do on your computer is usually converted to number before it can actually be processed by the computer. Even if you play a YouTube video, the computer does not understand anything that is going there. Everything the computer is seeing there is just number. It just needs to be adding, subtracting, multiplying. That's all that keeps going on in the background. So what about the data set that contains maybe pictures or alphabets or text, or even videos. So how does the computer actually sees these things that are not actually numbers? So that is where featurization comes into place. Featurization is the conversion of all the data types into numbers, integers that a computer can actually use. And this conversion is done by the computer itself in your data pipeline before it proceeds to process, manipulate, and learn from your data set containing things that are not numbers. So by understanding the data set and featurization, you can see how a machine can learn from and process data it receives to perform intelligent tasks. Now, this is a visualization of a data set. Now, you notice that we have X, we usually have it in X and Y. This X here these X are called independent variable, while Y is called the dependent variable. The Y is what we are trying to predict, is what the machine learning is trying to predict, while the X is what it is using to predict Y. The Y can be any kind of prediction. It can be numerical prediction from minus infinity to plus infinity. It can be as large as anything. It can also be a categorical prediction. It can also be a binary prediction, either true or false, yes or no, 1 or 0. So those are the three main types of predictions that we have in AI, and it is determined by this Y that you are seeing here. The X and Y are all contained in your data sets, like your comma separated value, CSV file. Or it can also be in Excel. It can be in an Excel format. If you have seen an Excel format, you will note that it's just a table containing all your X and then the Y that you're trying to predict. Now, all of these are called, this X1, X2, X3, they are called the features. The features are the things that the machine learning is trying to manipulate and see if it can use it to make prediction on this Y, the dependent variable. The reason they are calling it dependent variable is because it's depending on the features, the X. These are independent variable. They are independent. They are not depending on anything. They are on their own. They are standing alone. They are being used by the machine to make a Y prediction, if that is clear. So that is the number one. This is the data set. Now, just as I said, the X represent the features, Y represent the label. There, the Y is also known as the label, what you are trying to predict. So now this option 2 here, this number 2 here is the algorithm that is trying to determine the function that fits the data set the most. Now, anytime you hear the word algorithm is just talking about the mathematics that is happening in the background, which the machine will use to determine the best function that will fit all the data sets the most. Let's open this. So I'm going to open this. I'm going to share this window now. I'll share another window now. Good. So now we are sharing a different window now. So now, all this line, this green line you are seeing here is a function. This red line you are seeing here is also another function. This blue line you are seeing here is a function. The black line you are seeing is also another function. So now the question is, how does the computer knows the best line to pick there? It will know by using the MSE, the mean squared error, that formula that I showed you in the previous slide. Now, how does it do this? It does this by making some changes, some random changes initially of M and C. This M represents what? The weights, and the C represents the bias. This is machine learning terminology. But if you are using mathematical terminology, you say the M represents the slope or the coefficients, while the C is the what? Is the intercept. It's called the y-intercept. But in machine learning, we call the C the bias and the M the weight. So it keeps changing the weights and the what? and the bias until it gets the line that perfectly touches almost all the points on the graph. That perfectly touches almost all the points on the graph. Now, let me give an example for you to really understand the relationship between the slope and, let me share this window. Now, let's give an example. Now, look at this. This is an actual graph here. Now, let's take a look at this blue graph. Let me delete some of the things that are there. Now, let's take a look at this. Good. Now we have only the blue graph here. Now the blue graph has a weight of 2 and a bias of 3. This weight of 2 is talking about the slope of the what? Of the function. The function is this line here that is determined by this formula. Y is equals to 2x plus 3. So the slope is 2. Y, the intercept is 3. The intercept is the point at which it crosses the y-axis. The slope is just talking about the y dx. The y dx means the rate at which y is changing with x changing also. That is the slope, 2. Now, I want you to notice something. You notice that in this second function, f2, the slope increased from 2 to 3, or the bias increased from 2 to 3. Now, let's make this visible. Now, did you notice what changed? When you increase the slope from 2 to 3, what happens? This line becomes turned towards the left. That is, the slope has increased. Now, imagine a car is moving down this road. Imagine a road is actually inclined this way, and a car is moving down. The car is going to be moving down at a really fast speed because of the way the road is sloped down. Now, compare it to when a car is moving down on this slope. The car is going to be moving, is it going to be faster or slower? Obviously, the car is going to be moving down faster because the slope is even higher than it. It's more bent downwards. That's why this line is actually bent towards the left than towards the right. Now, what's going to happen if I reduce the slope? The road is going to be much more straighter. Now, let's look at this. Let me make this visible. Did you see what just happened now? The road became even less slopey. So if there's a car that is moving down this slope, it's not going to move down as fast as if it's moving down the blue slope down compared to if it's moving down the green slope. Now let's even reduce the slope even further. Did you see what happens when I reduce the slope even further? I reduce the slope to 0.1. See, the road is now more straight. It's no longer bending down again. So if a car is placed here, the car is not going to move down as fast as before. So the slope is literally what it means. It's just like a slope. The way the line is actually bent. Why this intercept? This intercept is just talking about the point at which it meets the y-axis. The y is the what? The dependent variable, what we are trying to predict. So now let's hide all other function and let's leave this. Now let's make the slope the same. The slope of the blue and the green, let's make it the same, 2 and 2. So the only thing we're going to change here is let's change the intercepts or the bias to 2. Now let's see what's going to happen. Now, did you see what happens? Did you notice that when the slope are the same, the slope of the blue and the green are the same, what happens? They are actually moving down at the same rate because the slope are equal. But the only difference is that the bias of this green is lower than it. So it's kind of shifts it downward. So that is what bias is. That bias is just talking about the what? The vertical shift of the function. I don't know if you get me here. If you understand what I just explained now, can you say yes? Let me know that you are not lost at this point.
Yes, sir.
Do you understand my
Yes,
explanation?
very clear.
Okay, very good.
Yes,
So
yes.
now, good. So now, what makes the AI intelligence is that we keep changing the slope and the intercept. It will continue to change it. It will continue having several trials of slope, several trials of intercept until it gets the best slope and the best intercept that fits the data points very well. based on the MSE, the mean squared error. Now let's go back to this window. So now, looking at this, looking at what is going on here, now we can, if you have noticed that all of these points here that you are having, they are what we call the data points. These are called the data points, and they are all represented in the data set, like the CSV, the comma separated value that I mentioned the other time. So now, let's say that we have this function red, this red function that is here, for instance. So how would the machine learn? The machine know that this red is better than this green line, for instance. This is how it's going to know. After it has plotted this green line, it's going to start taking all these points. It will look at the distance between this point and the green line, 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 this point and the green line. It calculates all the distance and squares it. It takes the value of that. Now, let's take this red line again. This red line, it does the same thing. It finds the distance between these points and the red line, this point 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 and the red line, all the points and the red line. It finds the distance between all of them and squared it. That's what they call the mean squared error. It squares the distance between all the data points and the line. We're talking about the vertical distance here, and then it squares it. So the one that is going to pick between the two will be the one with the what? With the lowest, the one that the mean squared error is closer to 1. 1 is the highest number of the mean squared error. 1 is the highest number that you can have in mean squared error. And if you can have 1, it means that your data is perfectly fitted to it. But if you are having a mean squared error of, say, 0.2, it's not well fitted. It means that it's quite, it's actually, okay, sorry, I made a mistake. 1 is not the highest. That is another, that is for R squared. That is for R squared measurements. R squared measurement is also another way for the machine to know that it has learned. Now we are talking about mean squared error. Mean squared error can be as large as 20 million. It can be as large as 30 million. The lowest mean squared error we can have is 0. That was a mistake. 0 is the lowest mean squared error we can have. So if you have a mean squared error of 0, it means that the line is touching all of the points and it is perfectly fitted. That's what it means. But if you have a mean squared error of, say, 1 million, it means that the line is very far away. For instance, let me give another line here. Let me draw a line of, let's give it, what color should we use? Okay, let's use this color. Let's use this gold color. So now let's say we have a line like this. Sorry. Now let's say we have this line of, the line is like this. Obviously, this is not a well-fitted line because it's not even touching any of the data points at all. So how the machine will calculate the mean squared error of this line is by taking these points, find the distance, take this point, 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 find the distance, and then square all the distances and see. You see that the answer we're going to get is going to be really, really large, which you would agree with me because you are squaring it. And you know, when you square a number, the number gets really, really big. So this is how a machine would know the best fitting line that explains most of the data points. So now let's go back to my slides. Good. So now that you've actually gotten how this thing works, how the algorithm works, now remember what I said, that a computer does like millions of calculations per second, which is not humanly possible. A human cannot do all those calculations as fast as a computer can do it. So this is the advantage of a computer doing calculations. It does it really, really fast. So a computer can quickly determine the best fitting line within fraction of a second. So that is what this number 2 is all about. The what? The algorithm. That's what number 2 is all about. So after it has determined the function that fits that set the most, now the theory is now going to be the model, which will now encapsulate the function that is derived by the algorithm for making the inference. Now, what do I mean by encapsulate? What I mean by encapsulate is that the function that we are talking about, like let's say y or fx, y is equals to 2x plus 3. That is the function that fits the data set. That function is going to be inside the model itself. So the model is not just the mathematical calculation alone. It contains other things like the data transformation that has been defined by our data pipeline. So all of these come together to give us the model. So if someone is saying a machine learning model, they are not talking about the algorithm alone. They are not talking about the function alone. They are also talking about the pipeline, the transformation that the data has gone through before the calculation is done and before the function is determined. When I say function, I mean the line that has been created for us, which is represented by y is equals to mx plus c. And we use this function for making inference. Inference just means that prediction. You understand? So now when you say y is equals to mx plus c, let's say y is equals to 2x plus 3. So now we know that let's say our x, for instance, is 3. And you said y is equals to 2x plus 3. So that means that y is equals to 2 times 3 plus 2. So whatever x would be is going to be slotted into that function itself that will determine. Let me open this again. I'm coming. Good. So now this is the function here. So now let's say we're trying to make an inference. Remember what we said an inference is just a prediction. Now, if a computer wants to make an inference, now the computer is trying to determine the value of y, for instance, when x is 2. So if I should put 2 here, it becomes 2 times 2 plus 3, which is 4 plus 3, which is equals to 7. That means our y will be 7. Anytime y is 2, somewhere here, what is going to be our x? Our x is going to be 7. Can you see that? Can you see what is on the screen? Anytime x is 2, what is y? Y is 7. It just puts it in the formula and make prediction. So the computer prediction is going to be 7. Why the input is going to be 2. The input is the question you are asking the computer. Why the output is the answer that the computer gives you. So if I should ask a computer that who is the president, for instance, most of you use ChatGPT. If you should ask ChatGPT, for instance, who is the president of Nigeria, ChatGPT might actually tell you that the president of Nigeria is Olusegun Obasanjo. Yes, that is wrong, but it can happen if the information was not in the training data that was used to train the AI. So the computer will just tell you that the president of Nigeria is Olusegun Obasanjo, thinking that that is the actual answer to the question based on the data set that it has worked with. If you did not train that AI with the current president of Nigeria, the AI would not know who the current president of Nigeria is. It's going to give you probably a old value that was in the data set that was used to train it. So that is exactly what is going on behind the workings of an AI. So now let's go back to the slide. Good. So now let's give another typical example. Now let's say that you're an artist event planner and you have been keeping record of all the numbers of attendees for all your events that you have organized for the past 10 years. You have been putting everything in an Excel spreadsheet. Now, in the column are those things that are standing vertically, like the column of an house. So in the column of the spreadsheet, this is going to take all the features. Sorry, I scrolled down so much. Good. So now in the column of the spreadsheet, that column is going to take all the things that you are considering, all the things that you have been recording. Let's say that you have been recording the day of the month, the day of the week, the month, and the top 3 artists, the top 3 popular artists that was invited to the events to perform at the events. And then the price of the tickets too is also part of what you have been recording, and whether or not the event was advertised on Instagram, Facebook, Twitter, TikTok, or DSTV Music, and then the location. All of these things I'm saying are the features, and they are represented by X. So the day, let's say now, the day of the month is going to be X1, the day of the week will be X2, the month will be X3, the top 3 artists will be X4, X5, X6. The advertisements, if it was advertised, if it was advertised or not, can be X5. The price of the ticket, X6, whether or not it was advertised on Instagram, X7, X8, X9, X10. So these are all of the information that the computer will try to use to make a prediction. Now, for this event planner to actually predict the number of people that will attend his events, what is he going to do? First of all, he will need to convert this Excel spreadsheet to a format that a computer can easily read, which is usually the CSV file, the comma separated value file, and then ensure that and label are all well annotated in the data pipeline for the machine to know what each column. Now, data sets, just as I said, will be represented as X1, X2, X3. That's what represents all the column that has been recorded by the event planner for the past 10 years. And then we're not going to see how these features will be used by the machine learning to make a prediction of the amount of people that will attend that event. So this is going to be a regression problem. It's a regression because what we are trying to predict is a number. We are trying to predict the number of attendees. It's not categorical. Categorical can be if maybe you are not using an actual number to actually predict it. You are trying to predict something else. Maybe you are trying to predict if a man will attend or if a woman will attend. That is categorical. So this is going to be a regression, and it's going to be a regression problem because you are predicting numbers here. So this is the basic idea of how a machine actually learns. It's trying to find the best function that will fit most of the recorded values you have. And how does it find the best function? By using the mean squared error, the one that has the least mean squared error, the one that the mean squared error is as close to 0 as possible. So now let's look at this diagram here. This diagram is just classifying machine learning into the different subtypes. Now we have supervised machine learning and we have unsupervised machine learning. Supervised machine learning just means that there's a there's a dependent variable, which is y, in your column, in your data set that you are using to train the AI. That's just what it means. Is supervised is because, what do you mean by supervised? Remember that if a child is learning how to walk, what happens? The mother would try to hold the child by the hand so that the child doesn't fall off. So this is a form of supervised learning. The child is being taught how to walk by showing the child an example of how to walk. So the child has a reference already. And the reference in this case is the data set. So every time the machine learning goes through this entire data set, it tries to use that bias and intercept that I'm talking about, that is the slope and the intercept, or the bias and the weight. It's trying to use it. It will be changing the value of the bias, it will change the value of the intercept, and see the one that is close to getting this y value as much as possible. So for this class, we're only going to be talking about regression, actual number. Like what you can see here, you can see 3 ice creams there. These lights, yeah, you can see 3 ice creams here. Okay, this one is trying to use 3 features: the time of the day and the temperature to determine how much ice cream children are going to buy in that day. So this particular one has just two features. It has the temperature of that day and the day of the month to determine how much ice cream children are going to buy on that day. Obviously, if you think about it, on days where it is very, very sunny, most people are likely to buy ice cream because they are trying to cool their temperature. And on days where it is cold, nobody will want to buy an ice cream. So you can see that we can already determine, by using our own intuition alone, we can already determine the relationship between temperature and the number of ice. The other feature there, the day of the month here, you can also use that to determine how much ice cream is going to be bought on a particular day. It might not be easy for a human being to make that calculation, but a machine can easily determine that, okay, probably on the 6th or maybe on Saturdays, people used to buy ice cream more than on weekdays. On weekend, people tend to buy ice cream more than on weekdays. Or maybe on Monday, people tend to buy ice cream more for their children than on Wednesday. Probably because they just started school and they are not really happy about going to school, and maybe their parents are trying to encourage them by buying more ice cream for them. It's something I just thought about now. So I'm trying to use my intuition to understand what is going on and how I can make a prediction, an intelligent prediction. On this Monday, when the sun is very high, I'm going to get plenty ice cream bought from me today based on this diagram here. And there's also, under supervised learning, we also have classification. Classification can be binary classification or it can be a multi-class classification. An example of binary classification is either male or female. That's an example of binary classification. Can be positive or negative. Maybe I'm trying to determine someone is HIV positive or HIV negative. That's an example of binary. It can also be true or false. Maybe you are trying to know whether someone passed an exam. It's either you pass your exam or you don't pass your exam. That's binary classification. Multi-class classification is when there are different classes. For instance, dogs, dog breeds. If you are trying to determine the class of a dog, there are so many breeds of dogs. There's Chihuahua, there's Rottweiler, there's German Shepherd, there's Boabu, and so on and so forth. There's Dalmatian. So this is an example of a multi-class classification. For unsupervised learning, remember that I say in unsupervised learning, we don't have a label. That is, we don't have a dependent variable. So the machine just goes in there and just looks at the data itself and trying to see how it can group the data into different categories based on the characteristics of the data set itself. So it's not looking at any label whatsoever. That's why it's called an unsupervised learning. So that's the difference between supervised learning and unsupervised learning. So let me know if you understand my explanation at this point. I'll love you to indicate that.
Yes, sir.
You understand?
Understand.
Okay, very good.
Yes.
So now we
Yes,
are
sir.
going.
Understood.
Okay, good. So now we're going to.
Yes,
Good.
I joined the class. Very, very interesting.
All right, very good. I'm happy. So now let's go to featureization. How does featureization work? So now that you have established that computer needs data in numerical form, specifically binary numbers, zeros and one, to process and learn. Now let's dive into the process of featureization. Featureization is the process of transforming raw data into numerical features that is used by a machine learning algorithm, which is just mathematical calculations. Now, this step is crucial because it allows the computer to interpret, analyze, and learn from the various forms of data, be it a text, be it an image, an audio, video, anything it may be. It needs to convert it into binary numbers. Now, there are steps that you need to take before. There are steps that are involved in featureization. There's data collection. Data needs to be collected. This is the data that the computer will use to learn. This is what the data is. This is the data that the computer is learning from. We need to collect the data. There are so many ways we can collect data. We can collect data from sensors, like my smart wristwatch measures my health data. It measures my blood pressure, doesn't measure my blood pressure. It measures my pulse, my heartbeat. It measures my stress level. It measures the number of steps I take. It measures the number of calories I've burnt. It measures so many things. So this is an example of a source where we can get data from sensors, from your smart devices. Even your phone has sensors. Your phone has some step counters, which is a sensor. Anytime you are taking steps, your phone is counting the number of steps you have taken. You can also get data from a database. An example of a database is this our SQL Server. Microsoft SQL Server. Actually, Microsoft SQL Server is known as a data warehouse, like technically it's a data warehouse and not necessarily database. A technical database can be accessed, Microsoft Access, or you can even get it from the internet. You can go on Google, you can go on Twitter to source for your data. This data collection can also be done by scraping, also called web scripts for collecting certain types of data. These are just programmed into it to get it. It can come in different formats like text, files, images, audios, or video. Now, after collecting our data, we need to clean it. We need to clean the data. Now, what does cleaning data involve? It involves removing irrelevant data, removing noisy data, handling missing data, and correcting any inconsistencies or malformated data. For instance, let's say that after collecting our data for any reason whatsoever, now let's go to this data set. Now let's say that on this column here in our Excel spreadsheet, for instance, what is meant to be there is, let's say, the price of tickets, using that our event planner event, for instance. So let's say this X3 here, this column here is the price of the ticket. And in one of these data that you've collected, you are having something that shows false there. You know that there's a problem with that particular data. Is having false. The number of tickets cannot be false. It must be in number alone. So this is an example of a malformatted data. We need to either remove that or find a way to replace it with something else. So this is an example of cleaning data. It's inconsistent. Our data needs to be consistent. Whatever is on the column must be in every instances of the column. If it is true or false, everything must be true or false. If it's ones and zero, everything must be ones and zero. As a matter of fact, if it's even a whole number, you cannot have decimal numbers in it. If you have been having 1, 2, 3, 1, 2, 3, 1, 1, 2, 2, 3, 3 on a particular column, you cannot go and put 0.25 there. It's going to see it as a malformated data because the computer approaches all these data formats differently. The way a computer will approach integer is different from the way it approach a decimal number. An integer is a whole number. Good. So after you have done the data cleaning and everything looks well arranged and formatted, you will now go to the data transformation itself. Data transformation, as we said it, is how you break down things into actual numbers itself. Now let's take a text data, for instance. Now, let's say text is often transformed using techniques like tokenization, which breaks down the text into individual words or tokens. These tokens are then converted into numerical values using method like bag of words. This one just counts the occurrence of each text in a word and represents it by a value. You can also use the term frequency, inverse document frequency. This is also another technique for putting a probability on each number, which is meant to measure the importance of the word in the document relative to the entire collections of the documents. You can also use word embedding. Advanced method like word2vec glow represents words in a continuous vector space. What continuous vector space just means that the words are represented as vectors. A vector is an array of number. So if you have a number like 1, 2, 2, 1, 0, 1, 2, 3. This is a vector. If you remember in secondary school, they defined vector as anything that has dimension and direction. So if it has dimension like those individual numbers and it has a particular dimension, that is, it's going in a particular direction, we can call it a vector. So other example, a higher vector form is a matrix, because a matrix does not only have a dimension, it has a direction also. And it's also in a 2D format, a two-dimensional format too. For instance, let's look at the word king and queen. They might have vectors that are similar, but different in specific dimension that captures the gender. This will allow the model to understand and capture the relationship between king and queen. Remember what I said, that everything is converted into numbers in a computer, and that numbers it doesn't even necessarily have to be an integer. It doesn't even have to be a float. It can be a vector. It can also be a matrix. Yes, it can be a matrix. It can also be a 3D array of numbers too. Whatever the complexity of what you are representing is, that will be the complexity of the representation of that thing may be. For instance, this king might be represented by a 3-dimensional array. The queen can also be represented by a 3-dimensional array. So when it compares king and queen, the machine will be able to see how king and queen are related to each other based on this 3-dimensional array. This is known as the continuous vector space. Now let's talk about the image data. The image data are converted into numerical matrices where each pixel represents the intensity of light. There are different techniques for doing this, such as resizing, normalization, and CNN, convolutional neural network, that can be applied to extract features. So remember what I told you about images. Images are just pixels that are placed beside each other. If I should zoom in, let me see if I can zoom into this. Okay, good. If I should really zoom in into this very closely, it starts to break down into its individual pixel. Okay, we can't really see the pixel here. Okay, let me zoom into this because this is an actual image. I'm coming. Good. You can see that it's becoming less and less clearer as you are zooming into it. It's becoming less and less clear. This supervised learning that you are seeing here, all these small things, all this black stuff you are seeing here are just pixels. They are small, tiny boxes of colors that are placed beside each other. But it's because you are looking at it as a whole. That's why you are not seeing those tiny pixels. But the computer is going to see each of those pixels and is going to convert it into what? Numbers that it can manipulate. The same thing with audio data too. Audio files too can be broken down into samples. Samples just means that a combination of different magnitude. Like as I'm talking right now, there are vibrations that are coming out, that are being transmitted through the air to my audio sensor of my laptop, of my phone. So my phone then converts all these vibrations into a data that it can understand and then sends it over the internet and sends it to the phone that you are using right now to watch this webinar. And then your phone will then interpret this data back to the audio that you are listening to. So this is how data is being transformed. Like the audio data is just being broken down into samples. Now let's talk about categorical data. For instance, colors and types, that type of categorical data. There are different ways how they can be converted. They can use one-hot encoding. They can also use label encoding. For instance, let's look at this. We have 3 categories. We have red, green, and blue. Red can be represented by 100, as you can see. Green can be represented by 010, and blue can be represented by 001. You can see that each of these numbers are represented by vectors. Remember I said vectors have magnitude and direction. You can see that they have magnitude 001, direction going in this way. So this way, the computer will be able to have something that it can use to represent red, 100, something it can use to represent green, 010, something it can use to represent blue, 001. So all of this representation can be manipulated by the computer. So now that we have all of this, instead of seeing red, green, and blue, the computer is seeing all these vectors, and it can easily perform calculations on it to make prediction. And it can also be labeled encoding too. Labeled encoding just means putting a whole integer, like representing red with 1, representing green with 2, and representing blue with 3. But this is not advisable. The reason why label encoding is not advisable is because if you are using 1, 2, and 3 to represent the colors, for instance, the computer will think that blue is bigger than green and green is bigger than red, which is not true. We all know that blue, green, and red, they don't follow any particular hierarchy. So they are not bigger than any. They are not bigger than anyone. So you see that there's another method that is being used anytime there's an hierarchy. Now, the best time to use this label encoding is when there's an hierarchy. For instance, educational level. You can represent high school with 1. You can represent in college with 2. You can represent undergraduates with 3. You can represent grad school with 4. You can represent graduate degree with 5. You can represent PhD with 6. So this will make sense for the computer to know that, yes, PhD is bigger than high school, or undergraduate degree is bigger than high school. And there's also feature scaling too, which is scaling the data within a particular range. I think we have actually spent more than an hour. Okay, so we are going to continue from the next class. We stopped at feature scaling. So I hope you understand all my explanation up to this point. If you have any questions to ask me at this point, please feel free to ask me.
Okay, thank you very much, Adedapo. If you have any question for him, please go ahead and ask.
It looks like my explanation is very clear.
Oluwa, I can see Oluwademilade.
Okay.
Oluwademilade, please unmute and ask your question.
All right. Thank you so much, sir. Thank you, Mr. Dapo, for this learning session. It has been really insightful. So quickly, I just want to ask if you're going to give us access to the notes,
slide,
just so we can read that, to get to the slides, just so we can read ahead and then.
Yes, you can. Yes, yes. The link has been sent. The link is accessible by anyone, anytime you want to access the link. So this slide that I'm going through right now.
All right.
So these notes, these.
Okay, Oluwademilade, are you on our WhatsApp group?
Yes, I am, but I tried to check the group. I didn't see it. It was probably sent before I joined the group.
Sorry, I couldn't hear you. I
said I tried to check the group. I'm on the group, but I tried to check. I think it was sent before I joined the group.
Okay. Don't worry, I'm going to reshare it.
All right.
Okay, where is
Atilade wants to ask the question.
Okay, Atilade. Okay. Atilade, please go ahead and ask your question, please.
Okay.
Hello, Atilade.
It looks like she's off.
I think he's still on the call. Maybe he's trying to unmute.
Or maybe it was a mistake. Maybe she's raising her hand by mistake. I think Rita wanted to ask a question.
Okay.
Yes, I actually wanted to ask a question. Good evening. Can you hear me?
Yes, I can hear you.
Okay, I'm very sorry. My network is pretty poor, so you might be getting delayed response. Anyways, when you were talking about the feature scaling, I did not understand. So if we want to use the feature scaling, do we have to put the data set in do we have to categorize the data set?
For feature scaling, no. We don't scale categorical data. We only scale numerical data.
Okay, just numerical. No, because you were giving examples using high school, secondary school, and PhD, and you were talking about the hierarchy. That's what I was asking.
Oh, that
I
is
thought that
not
was why
scaling.
you were using that.
That is not scaling. That is not scaling. That is called encoding.
Okay.
That is encoding.
Encoding. Okay. All right.
Yes,
Thank
encoding.
you. Thank you. All right. Thank you very much, sir.
But I hope my lecture was clear. I hope it wasn't too complicated for anyone.
It was super clear, sir.
All right. I'm
Okay.
glad.
Please, do we have the recording of this so that we can always go back to it?
Yes, I'm going to share the recording on the. Are you on the WhatsApp?
Thank you so much. Yes, I am. I am.
Okay, good. Oh, so I think we should appreciate Adedapo. Let me tell you
I
one
really
thing that.
appreciate you, sir. Thank you very much, sir.
Yeah, you're
Okay.
welcome.
Let me tell you
Your
one
class
thing
was
that.
so easy and simple. Thank you very much.
Yes. He has broken down. Let me tell you one thing about his approach to teaching machine learning. You know, a lot of courses out there, they just start coding, you understand, and people are confused. And, you know, one thing about machine learning is that the fundamental of machine learning is mathematics. And those basic things that I need to know that really will help you to have a good foundation in machine learning. He has, you know, his approach has really unveiled that. So I'm very sure that if you are consistent with the class, you are going to, you know, it's going to demystify the, you know, a lot of people run for machine learning and won't deceive you, but they thought it's very hard, and probably it's because of the kind of exposure they had, you know, but, you know, I would say that you are really unfortunate to be under this kind of teacher, because you are really broken down the concepts into the smaller, as in the minutest units that
Yes,
anybody
yes.
can
I'm really
understand.
glad. I'm glad you
Yes.
all found it to be very
Yes.
simple.
And let me also confess, I'm also, even though I know I'm a bit advanced, but you know, this concept, it's a lot of times I have to come back, you understand, to learn the mathematical behind all those models that we built. You know, I'm also gaining something. Everybody is learning. So thank you very much, Adedapo.
You're welcome.
And,
You're welcome. Thank you. Thanks for the attendance. I'm really happy with the number of attendance too.
yes. We hope that we keep increase the
To
advertisement so
increase
that
the
people can.
participants, that would be really great.
Yes.
So we can have more questions because I like questions a lot.
Yes, I can see that you like questions, you like challenges.
All right.
Thank you very much.
So I'll see you guys in next class for feature scaling.
By Friday evening, we are going to be having the next class, 6:30.
Yes.
Okay,
Yes.
so good evening, everyone. Have a good evening, everyone. Bye.